Now, here's a problem that's similar to the concept of a ballistic pendulum. Okay, it has a totally different geometry, but the analysis and the steps are the exact same. Okay, so here's another way you could find the speed of a bullet without having a high-speed timing device like a photo gate. Okay, so instead of having the ballistic pendulum where you fired the bullet in, the pendulum swung up, here I have a block of wood. Okay, let's say it's laying on a wood floor. All right, so this is my before picture. So I fired the bullet into the block, okay, and then the bullet is my after picture. The bullet immediately embeds itself in the block. They both begin to move off with some common speed, big V, and then they slide some distance across the rough floor and then come to rest. So imagine doing this like on a gymnasium floor where you fire the bullet right here, it goes into the block, and it slides and it comes to rest. Okay, so I want to find the initial speed of the bullet, and I'm given some information up here on the top. Okay, so the steps are going to be the exact same as the ballistic pendulum, but totally different geometry. This is in a straight line. Okay, so for the collision, okay, here's my before picture. I conserve momentum for the collision. So P initial equals P final for the system. Remember, the system is the bullet and the block. Okay, so P initial is for the bullet. Okay, P final, there's my after picture, is the bullet is embedded in the block. So the total mass is M plus big M. And then they move off with some common speed, big V. Remember, momentum is mass times velocity. So M plus M is the mass of the bullet block system, and that capital V is the speed with which they both begin to move right after the collision. Okay, I'm trying to find little v0. Okay, so same idea as a ballistic pendulum. I'm trying to find little v0, but I don't know that capital V. So now I have to find that capital V. Okay, so we can't say that the initial kinetic energy of the bullet here, okay, is equal to the final energy over here. Okay, energy is not conserved because what type of collision is it? It's a perfectly inelastic collision. Okay, these things stick together, so most of the energy is dissipated in the form of heat. All right, so just like the picture we had before, okay, the bullet embeds itself in the block, okay, drills a hole. So while the bullet is in the block, you have these backwards kinetic friction forces that's all around the outside of the bullet as it drills itself into the block. So most of the kinetic energy is dissipated in the form of heat. So what we do is we say immediately after the collision. So the collision happens quickly. So this picture, okay, that picture there, is after the bullet is done drilling a hole. Okay, so the bullet drills a hole quickly, and the system begins to move with kinetic energy. So after the collision, okay, we use our go-to energy expression. I wrote it right here. Okay, that's the one we had from our previous chapter. So the only way the energy can change is if there's some non-conservative force that helps to speed it up or slow it down. It does work. Okay, or energy is lost to kinetic friction. Okay, now let's ask this one. Are there any non-conservative forces that act on the bullet and block? Yeah, you have normal force. I'll just draw that one. Okay, does a normal force do work? No, because it's perpendicular to the displacement. So there are no non-conservative forces that do work, okay, like the normal force, but there is the kinetic friction force, right? That's a non-conservative force, all right? And we don't talk about the work done by friction, but we can quantify the energy lost. Remember, that term, energy lost due to friction, is F sub kd. Okay, so I'm using this expression. My change in energy is E final minus E initial equal minus E lost. Okay, and I just brought the initial over, and that's what I have. Whoops, that's what I have right there. So E final is equal to E initial minus E lost. Okay, and I'm using, this is my E initial picture, that's my E final picture. Okay, so my initial energy, oh, I'm sorry, I'm doing right here. This is, I'll put it here. This is E final is equal to E initial minus E lost. Okay, all right. So my final energy, okay, final energy is 0, right? Because it comes to rest. Final energy is 0. So that says all I have left is E initial minus E lost is 0. So that's why I wrote that. So E initial is equal to E lost. So initial energy is all kinetic. Final energy is 0. Where did it go? It was lost. The kinetic energy was dissipated due to the kinetic friction force. So right here, I have E lost is F sub kd. Okay, so this whole expression, I'll do it one more time. That whole expression, E final 0, so I have E initial equal E lost. So my initial energy is all kinetic. Okay, remember kinetic is 1/2 mv squared. So it's m plus big M, because they're stuck together. That's the speed with which they both start to move, okay, right after the bullet embeds itself, right? And the energy lost is F sub kd. Okay, but the kinetic friction is always mu sub k times the normal force. And you could look at the picture up here, okay, and the normal force is just m plus mg, right? Normal force is the weight of the bullet and block. So right there, where I have F sub k, I put in mu sub k times the normal force. Then don't forget the distance d, right? That's the distance it slides. I know I have delta x in the picture, right? But that's the distance that it slides. Okay? So the m's cancel out, okay? And I can solve this for capital V. And then I take that capital V and I put it right there, okay? And then solve that for little v0. Right? So just like the ballistic pendulum, I can find the speed of the bullet without having to have a high-speed timing device. So I can measure the mass of the bullet, I can measure the mass of the block, okay? I can maybe take that wood floor or a piece of that wood and I can do an experiment like we did in class where we tip something up and we had the bullet and block slide down at constant speed to find mu sub k. Remember, if it went at constant speed, mu sub k was tangent of the angle, whatever that angle was that allowed it to move at constant speed. G we can measure, and I can measure the distance d. Okay, so different geometry than a ballistic pendulum, but the exact same steps. Conserve momentum for the collision, conserve kinetic energy after the collision, all the way to where it stops moving. Well, I shouldn't say conserve energy. Use our energy expression. That's our energy expression. Okay, so another way to look at collisions, all right, is this is what I had drawn before. I had mass 1 hitting mass 2, all right. So we talked early in the force chapter is that you can think of a force as some type of interaction. So here I have a collision force. It's an interaction. It's an exchange of forces. And so we're going to see this word impulse pops up in this part of the chapter. So here I have two objects coming at each other, okay, and this one's small and slow, this one's large and fast. This is my before picture, okay. This is my during picture. Right? So over here, I graph the collision force versus time. All right, so right over here, okay, they haven't collided yet. That'd be over here, no collision force. As soon as they start to touch, there's a collision force, right? And now the collision force can be a function of time. So as these things start to meet, okay, the collision force can get bigger and bigger. And you may have remember that when you did your projectile motion lab, when you had a spring, when you compressed a spring, the farther you compress the spring, the more force is required. So you can think of these two objects as two cars coming at each other, okay? They haven't touched yet, so that'd be over here. And then right when they start to touch, right when that one is right there, okay, they start to touch, the closer they get, the bigger the spring force is, okay? And then they get as close as they're going to get. That's where the maximum collision force would be. And then they start to peel away, and that collision force gets smaller and smaller, all right? Or you can think of this as a side view, okay? This could be maybe a side view of the ball, and that's a bat. So where the ball collides with the bat, okay, the ball deforms. So the ball starts out like that, okay, when it hits the bat, and then it starts to deform. Okay. So over here, this section of the graph would be before the ball and bat collide. This is where they first touch. Okay, this is over here. And then as the ball compresses as much as possible, that's where you have your maximum collision force, and then the ball and bat peel away from each other. Okay, so the collision force can be a function of time, right? We know from Newton's third law that these two forces are equal and opposite. Okay, the collision forces are equal and opposite, right? So we would say for the collision that the collision force changes the momentum of each object over some short period of time. So I want to calculate the change in momentum. Now we kind of already did this a couple of pages before that, but I want to calculate delta P. Start with Newton's second law, multiply both sides by dt, okay? And then we integrated both sides, we did this, all right? And this integrates directly to delta P. Okay, so this part of it we did previous pages. Okay, but now we're going to call this integral, the impulse. Okay, and it's kind of 50-50. Some books use I for impulse. Okay, we're not going to use I because in one of the next chapters we're going to use capital I for something else. So in a lot of books use capital J. So our books use capital J for impulse. Okay, so think of outside the context of the class, when have you heard the word impulse? Right? Think of when you're in the store, like an impulse buy. Right? You go to check out the counter. What do they put near the counter? Right? They put a bag of chips. Okay, so you don't go home and read the reviews of the chips over 3 weeks and decide whether or not you're going to buy the chips. Right? You make a quick decision. So impulse usually refers to something that happens quickly. Okay, so not really like here's your glider and there's your finger and you exert a force over 10 feet. Okay, or maybe you remember that lab where you had a glider and a string and the tension exerted a force over about maybe 80 centimeters. Okay, technically that's an impulse because you have a force acting, but impulse refers to a force acting quickly. Okay, like a ball hitting a bat. Okay, like a typical type of collision. All right. Okay, so you look at this integral. Okay, this concept of impulse. This integral is a measure of two things. Okay, it's a measurement of how big the force is, right? There's your force, and the duration of that collision force. All right. So the other thing is this integral here is also the area under the curve. So the area under a curve of the collision force versus time represents the impulse. All right. Now, that's a vector equation. So whichever direction the change of momentum points, we'll see an example. Okay. Well, actually, to say whichever direction the collision force is, that's the direction of the change of momentum, and whichever the direction the collision force is, because of the vector equation, that's also the direction of the impulse. So I'll show you an example. All right. Now, here's a new quantity, impulse. All right. What are the units? Well, the impulse is defined as this integral. Well, that's a force, that's newtons, and time is in seconds. So impulse has the units of Newton seconds. All right. Now, the other weird thing is, well, impulse is the same thing as change of momentum. Well, momentum is mass times velocity. So you look at the units of momentum, you have mass times velocity, kilogram meters per second. So if I take the units of momentum, all right, and I convert them, I say, okay, in 1 Newton, I have a kilogram meter per second squared, and I cancel out the kilogram, the meter, 1 of the seconds, I'm left with units of a Newton second. So the units of momentum, kilogram meter per second, is the same thing as a Newton second. All right. So, and we'll see why it's customary to write momentum in the units of momentum, kilogram meters per second. Okay. And it's customary to write impulse in units of Newton seconds. Okay. Now, it wouldn't be incorrect to give momentum in Newton seconds. There's nothing wrong with that because it's the same Newton. They're the same units. But we'll see in the next example what the context for that is. Okay, so here I have ball comes in, okay, hits the bat. The ball comes into the right, bat hits the ball heads out to the left. All right, so we would say that the force exerted by the bat on the ball, okay, is to the left. So in the chapter, they would say the bat gave an impulse to the ball, or the bat delivered an impulse J to the ball. Okay, so here's the confusing part about the concept of impulse. Okay, in the previous page, we solved for delta P. Okay, we got that, even pages before that. Okay, and then we called this stuff the impulse j, right? So we have to ask, why do we have two different words for the same thing? So this integral, okay, called change of momentum, and the integral we also call the impulse. Okay, so back we did the projectile lab. During lab I said that sometimes the lab will ask you to write the speed, write down the speed, and then after that it'll ask you to write down the velocity. And your lab partner might ask you, aren't they the same thing? And we said that they couldn't be the same thing because we wouldn't have two different names for the same thing, right? Speed's a scalar, velocity is a vector, okay? Here we have two different names for the same thing. So the integral of the collision force times the time is called the change of momentum, and it's called the impulse. So why do we have now two different words for the same thing? Okay, well, the change in momentum, okay, delta P, it usually refers to the object whose momentum changed. So for example, you look at the ball. So the ball comes into the right, okay, and now the ball is now headed to the left. Okay, so the change of momentum refers to the ball. The impulse refers to the thing that caused the momentum to change. That was the bat exerting a force. Okay, so that's why we can have two different words for the same thing. So change of momentum refers to what the ball is doing, goes in to the right, goes out to the left. The impulse refers to what caused it. The bat exerted a force on it. Okay, so again, so this is a vector equation. Okay, so if I look at this picture over here, my force points to the left. Okay, so the force points to the left, that means the change of momentum points to the left. Okay, and the force points to the left, that means the impulse points to the left. So this arrow here represents the direction of the force, the impulse, and the change of momentum. Okay, so that's what I did here is I calculated my delta P for the ball. So delta P is P final minus P initial, so MV final minus MV initial. So here's my MV final, okay? But the ball goes in at the same speed that it goes out at, just because I chose that, okay? So my V initial, okay, is minus V final, okay? So here I have to subtract two vectors. I have to do MV final minus MV initial. So what I did is I changed vector subtraction to addition. So instead of V final minus V initial, I did V final plus a minus V initial. Well, MV final points in that direction, okay, and minus MV initial points in that direction, because V initial points to the right, so minus V initial points to the left. So if I add these two vectors, okay, I get a big vector that points to the left. So delta P is a large vector that points to the left. Okay, so in that picture, change of momentum points to the left because the bat exerted a force to the left, right? And that also means that the impulse is to the left. Right? So again, you have one integral and you have two different names for that thing. So the change of momentum refers to the ball going in and changing direction. The impulse refers to the bat exerting a force over a short period of time that caused that change of momentum to happen, right? And then usually, and we look at these in the book, you usually have no idea what the collision force is as a function of time, okay? You have no idea what that function looks like, okay? So what they'll say is, okay, instead of writing F as a function of t, you have to consider the average collision force. So this expression then you might see instead of written as an integral, okay, they'll say there's your collision force, and that little bar over it denotes an average. So I'll do an example of this on the next page.